So our final speaker will be Professor Chris BOWEN. Let me share my screen. It's already here. Okay, so our final speaker today will be Professor Chris BOWEN. Professor BOWEN has a BSc degree in material science from Bath and a DPhil in ceramics from Oxford. Postdoctoral work has been undertaken at, sorry, how to pronounce this word? Tennessee University Hamburg and University of Leeds. He was a senior scientist at the Defense Evaluation and Research Agency from 1996 to 1998. He joined the University of Bath as a lecturer in 1998 and is now a professor of materials and former ERC advanced investigator. ERC grant agreement number 320963 on novel energy materials, engineering science and integrated systems. Research areas include energy harvesting, piezoelectric materials, bioelectrics, and functional ceramics. And his talk today will be on ferromagnetic materials for electrochemical and storage applications. So Professor Chris BOWEN, thanks very much for your sharing, please.
Thanks, Benedict. So I'll just share my... Oh.
Is it working?
Yeah, it's fine.
Excellent, it's working here.
So thanks everyone for and thanks Haito for changing your talk, so I'm not too lonely. So I'm going to talk about ferroelectric materials for electrochemical and storage applications. I'll make sure I'm finishing on time, so at 10:30. At Bath we work on ferroelectric materials. And Haito has provided a really nice introduction. So we tend to work on the ceramic materials. So at high temperatures, these materials are ionically bonded, and at higher temperatures than the Curie temperature, they're cubic. They tend to be cubic, so they're symmetrical. So there's no dipole and no piezo or ferroelectric properties. But below the Curie temperature, so at room temperature for many of the conventional ferroelectrics, we get a phase change and it's tetragonal. So we get a distortion. So now our titanium 4+ or zirconium 4+ in PZT, lead zirconate titanate, for example, is slightly displaced upwards in this case. So now we have a dipole in our material that we can exploit to get piezoelectric or pyroelectric properties. So this dipole can go upwards, the titanium 4+ can go downwards, it can go left, it can go right, it can go in and out of the page. So we have 6 potential polarization directions for this tetragonal unit cell. So now when we make these as bulk ceramics for devices, I'm in a mechanical engineering department, those dipoles are randomly orientated because that's the minimum energy state. So there's no net polarization and no net piezoelectric property. So if I applied an electric field to my randomly orientated structures, some dipoles would expand, some would contract, some wouldn't react at all. And so you get no net response. So to make our ferroelectric active, we have to align those dipoles within the material, and we do that with a poling process where we apply an electric field, a few kilovolts per millimeter, and some heat to allow those dipoles to switch within an electric field, and we align those dipoles. We then cool the material down with the field still applied, and then we take the field off and we have our remnant polarization and a macroscopic polarization across the material. And as Haito indicated really nicely, we work on ferroelectric materials because we can switch them exactly as I just showed there. We can apply an electric field and switch those dipoles, and all these ferroelectric materials exhibit a pyroelectric response because its polarization changes with temperature. And likewise, all these ferroelectric materials exhibit a piezoelectric response because, again, the polarization changes with stress. That's different to materials like zinc oxide and quartz, which can be piezo or pyroelectric, but they're not switchable. And so you have to use those in single crystal form if you want to get any net polarization. So once we've done that, I've got a little bit at the start really on sort of sensing and harvesting, and then I will move, I promise, onto electrochemical systems. So once we've poled our material, we can use it as a sensor or as an energy harvester. And so if I apply a compression, imagine pushing that titanium 4+ ion back into the center of that tetragonal unit cell, the polarization falls, and I develop a charge. Likewise, if I apply a tensile load, the titanium 4+ has moved even further away from the center. And so again, I'm enhancing the polarization, and I'll develop a charge for a sensing application or an energy harvesting application. And it's always interesting, and this can be at the device scale, or as Heito was explaining, can be at the particle level in an electrochemical system. It's interesting to know where this charge comes from in a way, because the material itself, the ceramic, is a dielectric, it's an insulator. So if I take my poled material, my polarized material, and I electrode it, or I have a surface, then I will collect opposing charges on the top and bottom surfaces of my polarized material. And that's because you want to get sort of charge neutrality. And there'll be no current, there'll be no potential difference across that device or across that particle. So it's only when then you apply a compressive load, you then change the polarization of the material. So some of that surface charge, that screening charge, is now free to take part in current flow. That could be a chemical reaction, but it could also be just as a sensor. And likewise, when I apply a tensile load, the polarization will increase and the charges will have to flow the other way to rebalance. So it's changes in stress that lead to the development of charge. And at Bath, we use that really for sensing and energy harvesting. So I'll show some electrochemical work in a moment. So we use that to generate small scale power, milliwatt type power within systems to power sensors, tire pressure monitoring, wireless sensors, for example. So tires are a good example. Lots of strain, lots of displacement. You can attach that to an inner surface of a tire and easily develop a milliwatt that can power the tire pressure monitoring system. And the motivation there is that you want to replace batteries. Imagine you're supplying tires to a fleet of thousands of lorries, each with their own battery powered pressure sensor. It becomes a real pain and real complex management process to manage those batteries and keep replacing them. And if all you needed to do was develop a milliwatt from the strain in the tire, then you've got a sort of fit and forget system. And cars are becoming increasingly more automated, self-driving systems as well. You want to move away from battery powered systems when you can. Just some very basics. Again, this can be at the device level, but I'm including it because it can also be at the particle level, as Professor Heito Huang has indicated. So if I take a poled element and I apply a stress to it, a piezoelectric effect, I'll develop a charge. So I know what my charge is. I can develop a charge that's linked to the D33 coefficient, the charge per unit force times the force. I know the relationship between my charge and my voltage. It's related to the capacitance of the material. This material is a dielectric, so it acts very much like a parallel plate capacitor. And so I can work out easily what the open circuit voltage is under a given stress. So it's proportional to the stress, it's proportional to the height, and also it's proportional to these properties, D33, charge per unit force divided by the permittivity. And this is interesting because obviously we need a certain potential to drive a reaction, or we also need a high potential to develop a good sensor. And the voltage is proportional to the height. And remember, it's the surface charge that you're collecting or you're using, and the voltage goes up with thickness because you're you're pulling those charges, surface charges, further away. So you're getting a bigger potential. The current, on the other hand, is different. The current is proportional to the area. And that's because, remember, it's the surface charge, the screening charge that you're collecting. So you get different effects. Voltage is driven by height and also D33 and permittivity. Current is related to area and just D33. So there's a variety of balances, and we'll see that in a moment. So for a good sensor or for a high voltage, this is what we want. We want a high D33 divided by permittivity in terms of material properties. And again, I work in energy harvesting. The energy generated is half CV squared. And so again, I can use this equation and put it in here. I have my very simple parallel plate equation. So I can work out the energy generated for an applied load. And again, it's proportional to the volume, proportional to stress squared. And again, these are the material properties, D33 and permittivity. So I want high harvesting figures of merit. So high voltage, we require D33 divided by permittivity. High energy, we want high D33 squared divided by permittivity. So similar, but some small differences. I've worked a lot on porous materials over the years. Benedict mentioned I used to work for the Defence Evaluation and Research Agency. So we were using those to make hydrophone materials. Large voltage means that we can use them as high sensitivity sensors. And by introducing porosity, what we're doing is reducing the permittivity of the material. So we're driving those figures of merit up. We have some very nice models at Bath now where we can model the polling process within these materials. Remember, we need to apply in a field to align those dipoles to get a macroscopic alignment. And the pores produce some complexities in terms of that polling process because the electric field will focus in and be concentrated in the pores because it's a lower permittivity phase compared to the ceramic. So the ceramic will be relative permittivity of 2,000-3,000. Air is 1, and so the electric field will be within the pores. You have to design the appropriate microstructure to mitigate against that. And certainly by making the material porous, we can get pretty large improvements in some of these figures of merit. So making a highly porous material, we can go from a dense material because of its high permittivity, which has a value of 900. Don't worry about too much about the units. It's just a figure of merit, a relative assessment of performance. But by making it porous, by maintaining the polarization, but reducing the permittivity by adding porosity, we can get down to up to 2,500, sometimes 4,000. And we do that by alignment of the pores. So we take our pore phase and we consider aligning the pore along the direction of the applied electric field. So in this case, I'm applying my polling field through the thickness of the material. And if I align my pore at 90 degrees to the electric field, because the field, it will focus in the pore, the region of ceramic above and below the pore will experience a low electric field, so it won't be polarized. So clearly there's a benefit by taking highly anisotropic pores rather than round pores and aligning them within the electric field to maximize my level of polarization and minimizing the low field regions around the pores. And that's where the link with Professor Yan Zhang at Central South University. She visited Bath as a Marie Curie fellow and introduced us to freeze casting, and that could produce these beautiful structures where you get exactly what we want, highly aligned pores within a specific orientation. We can now apply electric fields to this to align those dipoles, get very high polarization, high D33 values, but much lower permittivities because of the presence of the pores within the material. and create a wide variety of sort of sensors and energy harvesting structures. And by doing that, we can get the polarization even higher. So remember, the dense material was around 900, and the aligned porous materials factor of 4. So better in terms of energy harvesting performance, but also be improved in terms of voltage. Lots of people said, oh, figures of merit are fine, Chris. Does this actually work? Because you're removing material, you're removing the active material, but you're generating more energy, or you're generating a higher voltage. And so I had to prove that. So this is a porous material here on a shaker. It's got a mass on top, applying that constant load. And then what we do is we accumulate that charge as we change the polarization and put it onto a storage capacitor. So it could be a supercapacitor, it could be a standard capacitor, and see which wins. Is it the porous material that's generating more energy or generating a higher voltage? And it did work, and that's because the figures of merits do work. So this is the voltage against time as it's oscillating on the shaker. The blue is the porous material, 55% porous. The red is the more dense material, the standard material. And you can see that the blue porous material generates a higher voltage, and that's because of the lower permittivity. And so it's a better sensor, or if we had particles that are within an electrochemical system, we'd be developing a higher voltage. The current is reduced, but if we look back to our basic equations, that's not surprising, because the current is related just to D33. It's got nothing to do with the permittivity, and we won't be able to pole as well, making it porous. So we do expect it to fall, but power is a combination of voltage and current. And so when we look at the energy or the voltage stored on the storage capacitor, the porous ceramic wins outright. And I'll move on now into electrochemical systems. So a lot of cases in energy harvesting, we're doing that to develop low scale power and to store our power for wireless networks, milliwatts, for example. But certainly people are now moving, rather than having a storage capacitor, to use that harvested energy to affect an electrochemical process. So there's certainly work looking, as Haito has said, looking at pyroelectric materials, piezoelectric materials, again, when that charge and that voltage is used to affect an electrochemical reactions, water splitting, dye degradation, for example. And obviously people are doing that photovoltaics. You can do that at scale, obviously, for hydrogen generation, thermoelectrics, but obviously because the ferroelectric nature, I'll focus at the last bit of the talk on piezo and pyroelectric. I think this is work by Starr, and this is one of the very first bits of work on using piezoelectrics for water splitting. So I'd just like to mention that it's really some nice key sort of pioneering publications. And here it's a device. So again, it's a cantilever that's being oscillated when it's surrounded by water. And by oscillating that cantilever, you're generating a potential and you're generating charge. And Starr showed that you can indeed, in fact, induce some elements of water splitting by using the output of the energy harvesting device. In this case, it's hydrogen against strain, and it's the PZT material that was outperforming some of the other materials. I'll touch upon maybe why in a moment. That was followed by some other work looking at zinc oxide materials. Again, that's not a ferroelectric, but it's a piezoelectric material. So again, a coated piezoelectric wire that's been subjected to a force. And that's, as Haito was rightly saying, it's a semiconductor. So we have, and tuning the band gap as well. So it had a combination of piezoelectric and sort of photocatalysis as well. And work that I've been doing with Professor Ya Yang, he's been using composite materials where you take the ferroelectric material and embed that into a porous polymer foam And the pause in this case is really just to let the solution electrolyte to enter the structure. And it's in a polymer foam because you can then mechanically deform the material to develop those charges. And that was used by mechanical deformation to achieve sort of wastewater degradation of dyes, rhodamin B, for example, within the material. I think with mechanical deformation, it tends to be relatively low frequency. So a lot of the work on piezo-catalysis tends to be the application of ultrasound, and that's because it's much higher frequencies, 40 kilohertz, for example, a much higher intensity. Remember, it's the change in polarization that develops the charge. So if you increase the frequency of the oscillation, then you're going to develop larger charge, and the inherent sort of cavitation effects that you get within the application of ultrasound means that as the bubble collapses, as you apply ultrasound to your solution, that bubble collapse will produce very high pressures and also very high temperatures. So you're going to get much more significant changes in the polarization of the material, piezo or pyroelectric effects. I guess the challenge in a lot of the ultrasound experiments is it adds a lot more complexity to the experiments because you have sonochemical effects. So I think when people are doing this work, it's important to do control experiments, add non-ferroelectric particles, or add just the solution without the particles as well. And that's where we work with Professor Phuong in Vietnam Academy of Science, because there's very nice, careful control experiments to try and understand these sort of more complex systems. And I think the very early work, again, this is not from Bath, is by K. Hong, looking at application of ultrasound to zinc oxide materials. And there's Haito nicely explained, when you have these rod type structures, you induce bending, and that bending induces higher strain, which develops higher changes in polarization and more charge. And there's a lot of very nice sort of analysis of what sort of voltages. And I think a characteristic of these piezoelectric materials tends to be high voltages, even as a sensor or as a particle, high voltages. And so generating the necessary voltage for a chemical reaction is potential. But the downside is that they generate relatively low levels of charge. So they're high voltage, low charge, and how do you mitigate those effects? So at Bath, really just to try and understand the process, inspired by Professor Haito Huang, we looked at BST as a material. And I think I like the BST material, barium strontium titanate material, because it has a low Curie temperature. Remember, the Curie temperature is when it changes from a ferroelectric phase to a cubic symmetrical phase. And so for BST, it's about 45 degrees C. So this material changes phase from ferroelectric at below 45 to non-ferroelectric, a pyroelectric phase above 45. And what it allowed us to do is to look at the response above and below the Curie temperature, just to be sure that there's some ferroelectric contribution to what we're producing in terms of the chemistry of the system. So this is BST particles within a solution with the application of ultrasound. And this is just a series of ultrasound conditions where it's on and off, on and off. And by tuning that, we can tune the temperature. So this line here is the temperature. And I think what was nice is that when we get close to the Curie temperature, so when the system is close to the Curie temperature, this is the polarization of the material with temperature. So as we heat up our ferroelectric in the tetragonal phase, the polarization falls. As it begins to undergo a phase change to cubic, then there's no polarization. So that's the Curie temperature in a way. In this region here, very close to the Curie temperature, you'd expect the much higher piezoelectric activity, because it's very easy then to change the polarization with stress, and you also get much higher permittivities. A whole range of properties are maximized at this condition. And that's exactly what we saw when we changed the conditions of the experiments. We got better hydrogen generation when we operated near the Curie temperature. And obviously then when we exceeded the Curie temperature, then that sort of reaction rate or the hydrogen generation went down. And again, that gives us a good feeling that there's clearly some ferroelectric contribution to what's going on within the reaction. And the same happened also for dye degradation. So again, when we operated our system closer to the Curie temperature, when the material is more active, when the change in polarization under a stress is more easy, and so all these D coefficients increase more greatly. Again, we were getting better degradation of contaminants such as rhodamin B. Again, it also fell as we went above the Curie temperature. I got 15 minutes, so just the final sort of 10 minutes, I'll talk about pyroelectric effects. So piezoelectric effect is obviously a change in polarization with stress. The pyroelectric effect is very much the same thing, but it's a change in polarization with temperature. So again, if we imagine our poled particle, can be a ferroelectric material, a device, or even a particle within a solution. If we heat it up, then the polarization will fall. And so some of these screening charges on the surface of the material are free to take part in a current flow or to take part in an electrochemical reaction. And likewise, as we cool the material and the polarization returns or increases, then current will flow in the opposite direction to rebalance that charge. So again, it's very much the same effect. So all the ferroelectrics are both piezoelectric and pyroelectric. And again, some very early work. This is Ting Ting Zhao. Just put a pyroelectric material on the outside of a container that was heated up by an exothermic reaction. And that heat was enough to power a small LCD. I don't think this is a form of energy generation because it'd be very sort of inefficient. Professor Haito Huang was sort of indicating that maybe it could be some sort of self-powered system in a sort of chemical process. But again, it gets you thinking of what it could be used for. And as Haito mentioned, I was making devices, external devices, and I knew that they would generate high voltages. So could I actually use them to induce water splitting? So this is just a ceramic element that's being subjected to some heating and cooling. So the polarization is changing, is modulating as I heat and cool. These then surface charges from my external device are now free to take part in an electrochemical reaction. It's an AC. Remember, current is flowing back and forth as the polarization increases and decreases. So if I couple it to some microelectrodes, I'd prefer to have hydrogen or oxygen being generated on the same electrode. So this rectification circuit just moves my AC output into a DC output. So I maintain that. And again, we can use our very simple equations. So I can work out the voltage, again, proportional to thickness because you're separating those surface charges. It's proportional to the temperature change, and it's proportional to these properties, the pyro coefficient divided by the permittivity. And so by doing that, I can work out what sort of conditions or what sort of material I need to generate the 1.5 volts for water splitting. So I can tune the material and the geometry to generate 1.5 volts, but also I need to maximize the amount of charge. And well, that equation here, so I can maximize maybe the pyro coefficient, the change in temperature, or the area. So again, surprise, surprise, the charge is proportional to area. because it's that surface charge that I'm using. So there's a balance here. I need the 1.5 volts to get the reaction going, but I also need the charge to maximize the amount of hydrogen I'm producing. And so we had a very nice simple system, again, with this rectification. Just a lamp that heats on and off, heats on and off. And I basically chose the biggest material, biggest element I could buy commercially with the maximum area to maximize that surface charge that I'm collecting. Connected it with a rectification circuit to a microelectrodes. And you can do a very simple analysis. What sort of materials are best? Well, actually, this is the voltage for the required thickness. And so we need 1.5 volts. So this is 1.5 volts for 1 degree C change in temperature. So you need to see that lithium tantalate, lithium niobate are good. Surprise, surprise, these are used in thermal detectors. PZT, the material I used, is not very good actually in terms of voltage because of the high permittivity. But actually, I still only need 100 microns as a device to generate that 1.5 volts for 1 degree C. So for voltage, PZT is not great, but even a thin device will do it. For charge, it's slightly different. And the charge per degree C against area, PZT was pretty good. So very good here. PMNPT is even better, but that's a single crystal material, very difficult to source in large quantities. And so I chose PZT, the ceramic, in the end, because it can develop the voltage quite easily, and really I want to maximize the charge. And so this is a PZT lead zirconate titanate element, changing a few degrees C, 2 or 3 degrees C in temperature, but easily developing 5 volts. And so that was able to produce the hydrogen that was by the water splitting. But it's very small levels of hydrogen because it's small levels of charge on the surface. I think there's some bubbles here. They're very hard to see, but I was very excited to see that Haito Huang, when I saw this paper, he took the idea forward much better and said, well, rather than having an external device, why not maximize the area to maximize your charge by having a nanoscale material and actually putting it in the solution. So rather than an external device where A is challenging, the cross-sectional area, I just have to make it bigger and bigger by going from a dense material to a nanoparticle form. Then I'm maximizing that surface area and I'm maximizing that potential for charge generation. I think there's been lots of work that stemmed and originate. I saw Haito's work recently that was taking that even further. And there's lots of mechanisms there, as Haito was saying about the band gap. There's also just the straight voltage across the particles. But Arvin Kakiani does some very nice DFT modeling where he's predicting that the hydrogen is being split over a 180 degree domain where the polarization is up and down, and that splits the water. And then when you heat, this polarization goes, and then the hydrogen and oxygen is evolved. So there's a variety of mechanisms, still a lot of debate, and still a lot of discussion and work to be undertaken there.
Professor BOWEN, you have a couple of minutes, so we can spend some time for Q&A.
Nearly finished. I think I'm nearly finished. So what I'll
to your time.
That's fine. So I'll just talk on the last few slides. So I think there's lots of excitement in terms of pyro and piezoelectric catalysis. This isn't my area, but we're sort of looking at the literature in a way, and I think it's interesting where there's a lot of effort in terms of battery systems now, lithium batteries, for example, and there are papers that are looking at ferroelectric materials being used as additives within battery systems, and it seems to be within a variety of areas. Some are using ferroelectrics to sort of mitigate against aging mechanisms and sort of degradation mechanisms within batteries, And there's other reasons that people are adding ferroelectric materials are to enhance sort of iron conduction and lithium conduction within the material. And I think that's an interesting area in which ferroelectrics can be used as additive in such systems. And I think one of the most interesting areas is that these ferroelectric materials are high permittivity materials. And if you have a ferroelectric or a dielectric inclusion within your iron conductive matrix, there's this very nice work by Mayer that says, well, what you do on the interface is develop a space charge, and you develop a defect-rich region between your dielectric inclusion and your conductive matrix. And if you look at the Debye-Huckel length, that length of your defect-rich region has a strong relationship to the permittivity of the material. And obviously these ferroelectric materials are highly polar, so you have very high permittivities. Some materials it's 3,000-4,000, some other materials up to 40,000-50,000 relative permittivity, even very high, certainly even when you're close to the Curie temperature. So there's certainly some interest in adding ferroelectric additives, not really due to the piezo or pyroelectric effect, but really exploiting their very high permittivity properties and sort of the large space regions, especially when those inclusions begin to coalesce and to percolate through the system. And this is just some work from the literature by Yada. Again, it's not our work, where the barium titanate ferroelectric has been added as an electrolyte interface. And so that high permittivity region produces a defect-rich regions, which affects the lithium plus pathway and enhances the conduction. So again, I think there's interest there in using really the high permittivity properties of these materials in battery systems. And there's also some other work where it claims to be using the piezoelectric properties to enhance batteries as well. There's also work by adding ferroelectrics to batteries. So PVDF, if you're a battery person, is used a lot as a separator, and that's ferroelectric as well. That's a ferroelectric polymer, and people are made that piezoelectric. I guess the issue there is that these are small levels of charge. So how do they really compete against the charging itself? So it's small contributions, but maybe they can be used as a sensor, thermal or stress in terms of a sensing property. That's good. I'm finishing on time. That's good. Keep everyone happy. So there are many opportunities. So I'm certainly interested in porous materials, flexible systems. Yes, harvesting, but also I think there's lots of work now in electrical and chemical systems, and that's very exciting, especially seeing the plasmonic work earlier. Disinfection, water treatment. I think there's also sort of ferroelectrics as additives in batteries as well, I think is very much interesting. And I like writing, so I get involved in sort of lots of review papers. So I think these top two that I put in, or top three here, these cover some of the aspects I've covered in this presentation. So thank you, and thank you for inviting me.
Thank you very much, Professor Chris Bowen, for your interesting and fascinating talk on this topic. So the floor is open for discussion. Any questions from the audience?
I think people are tired. It's been at end of the 3 days.
It has been long. Yeah.
Okay. Chris, I asked a question. So can you go to the slide for the solid state electrolyte, which is a very old paper, I think.
Yeah.
No, the Mayer's paper. Yeah.
Oh yes, yeah. Yeah. Sorry. Yeah, I know what you're talking. Yeah, that's.
Yeah. So you see, I'm wondering. So here you show the different rich layer. So do you imply whether the ion conduction is more easier, right, in this different rich layer?
That's exactly, yeah.
So
carry on.
Once you get a percolated network, then the I connection can you get a conductive network, right?
Yeah, that's exactly right. So I think some of the early work just added alumina, and so that's a much lower permittivity material. And what they saw was by adding alumina, it didn't make sense, does it? Adding alumina to an iron conductor ends up getting higher conductivity than the base material. So it doesn't. So that sort of made it. Why is that happening? And I think Meyer's work is hinting that by having this dielectric in a conductive layer, you produce this defect-rich region around the particle. And exactly as you said, when it's large enough to percolate, you have these higher, more conductive regions. And I think the advantage of the ferroelectrics is, alumina has a relative permittivity of what, 10, whereas the ferroelectric materials, you're in the thousands or even potentially tens of thousands. So you're increasing that defect rich, that sort of space charge layer. So I think and there's certainly some papers that are hinting that these additives, these ferroelectric additives, are leading to better conduction processes. Yes, that's right.
Yes, I noticed this is actually quite old work, right? People add some ferroelectric particles, right, into a polymer matrix, so it can increase the ionic conductivity.
Yeah.
The lithium, particularly the lithium ionic conductivity. So, but at that time, I think the solid state electrolyte is not a hot topic. So, not many people notice those kind of publication. But recently, there is a renaissance of those solid state electrolytes. So people start to add ferroelectric particles, right, to those polymer electrolytes. So it become.
That's right. I think that's why it's interesting in a way, and that's why because I don't do much work on batteries, do very little, but I just thought that was interesting. And as a ferroelectrics person, I'm seeing, you can see, that you get more papers to referee, or you just see more, and it seems to be coming back based on this work that was done sort of 10, 50, even longer, a long time ago. So the Meyer's work sort of 80s, isn't it? So things. So I think that's right.
Okay, thank you very much.
Right, thank you very much. Any other questions? Okay, if not, sorry.
Thank you.
Another question. All right, if not, thank you very much, Professor BOWEN, for your interesting sharing. Thank you very much.